All right. So, any questions on homework? 109 and 111? What do you got? Wait, are you saying 109 and 111 on page 186? You got ahead of yourself. Got way ahead of yourself. Yeah, because I didn't assign anything off 186, right? Yeah. It's all right. Okay. It's not going to hurt you. It's not going to hurt you. What do you got? Which one? On page 170, 42. Number 9. Yeah, well, it is kind of just straightforward. Oh, by the way, I have to stay between the red lines if I want it to come up on video, so that's why these red lines are up here. We have 2a times a plus 2 plus 3 times a plus 2, right? And you're asked to combine the binomial, or sorry, factor this where we have a common binomial factor. So what you're supposed to see here is that a plus 2 and a plus 2 obviously appear in both terms. So if you look at the two terms, like this term and this term, since they both have a plus 2, we can factor the a plus 2 out. And then in the new set of parentheses, write down whatever was missing. So whatever we don't, once we pull the a plus 2 out of this, what's left, right? 2a here, and then what's left here is plus 3. And that's it. Now you could have it backwards. I think the back of the book has it the other direction. Now, yep, that's it. Now, technically speaking, a lot of students learn this, but they're not quite sure why they can do this. Or you're told, hey, if you see the same thing, just write it down, then just write the other two things in parentheses. And so I want to kind of explain, why it is that you can do this. So forget this problem for a second and just look at this. What if I wrote 2ay plus 3y? Forget that problem. And I said factor out a GCF. You would say they both have a y, right? You take that y, you'd pull that out. Then what would be left would be 2a plus 3, right? So that when you distribute y back through, you get this thing. Well, the problem up here is exactly the same as this problem, except instead of a y here, we actually have an a plus 2, the entire binomial factor. So that's like a y, that's like a y. We pull the y out, and then what's left is the two things here. So that's kind of what's happening there. Sure you're going to be all right over there? Okay. We've got some more seats. All right. Any other questions? Okay, so we're going to move on then. We were talking about lines last time, right? Section 2.2, and we did not get to 2.3. But we did talk about how to graph lines, didn't we? And we said that there were basically two methods, right? One was the intercept method. The other method was using the slope-intercept form of a line, right? So somehow putting the y-intercept and then moving up and over or whatever it took to graph. We're going to do a lot more of that today, all right? But we're going to throw in a couple of other things. So what I'd like to do is just start with problems, and then as we move through the problems, I'll put up any new theory or definitions that we need as we go, all right? Or formulas. So I'm working straight out of the book here. I'm picking problems that are very similar to what's going to be on your homework. First one I'm doing here says write the equation of this line in slope-intercept form. I'm just going to say slope-int form. Basically, that means you solve it for y. And then identify the slope and the y-intercept. And then finally, just graph it. So there's nothing new with this. We did this pretty much last class. Here's the actual equation, 4y minus 3x equals 12. So is this a line, first of all? Well, you kind of can assume it is because I'm telling you to graph the line, but how can we tell it's a line? We have x and y, we have an equal sign, right? We have a power of 1 on both of the variables. That means it's linear. So we know what we want to get used to is looking at something and knowing what it is before we even, like without being given instructions, do you know this is a line? Okay, so I want to write the equation of this line in slope-intercept form, which means I want to solve it for y. Then once I do that, I should be able to identify the slope and the y-intercept, and then I should be able to use that to graph it. So here we go. How are you going to solve for y here? Get rid of x, you mean get x to the other side, you mean? The x term? Okay, so when we say solve for y, we mean isolate the y term, which means the 4y, we're going to leave it here. We're going to move this over here by adding 3x on both sides. Now, technically, I'll write it down. We're adding 3x. Here, I can't add 3x to 12 because they're not like terms. These cancel out. I get 4y equals 12 plus 3x. Is that correct to write it that way? Yeah? Now what? Divide everything by 4, right? Both sides of the equation, every term gets divided by 4. So I can do that right here. Divide by 4, divide by 4, divide by 4. And I'll have y equals, what, 3 plus, now here this is, we could write it as 3x over 4, but we could also write it as 3/4 in front of x. And that x next to it really means it's up here. Now that's not the slope-intercept form of a line yet. Remember, the slope-intercept form of a line looks like this. I mean, it is, but it's just not exactly written this way yet. I just need to switch the x term and the constant, just flip them, right? So I'm going to take that and write y equals 3/4 x plus 3, right? Okay, so even though it's just 3 here, we need to make sure that we include a plus between it. And that's it. That's the slope-intercept form of a line. And from this, we should be able to identify the slope and the intercept. The slope is always the number in front of x, the coefficient of x, and the y-intercept is always the number by itself. So what's our slope? 3/4. What's our y-intercept? Is 3, right? So I've done 2 of the 3 things I've been asked to do, and now I need to graph it. So let's graph this line. So you draw your xy axes. I'm going to use mostly black here because black comes out the best on the video. Even though I have multiple colors, if I write in red on the video, you can't really tell it's red. So I don't think my phone's on silent. Hold on. All right, so where do I start to graph this line? The y-intercept, right? Y-intercept meaning you start on the y-axis. You go to 1, 2, 3 units up. You put a dot. That's 1 point on your line. All you need is 1 more. And to get to the other one, you use the slope. Positive 3 on top means you rise 3, right? You rise, that means you're going to go up 3, and then your Number on the bottom tells you which way to go, left or right. If it's positive, you go right. If it's negative, you go left. So I'm going to run. That means I'm going to go to the right 4. So go from that point up 3, 1, 2, 3, to the right 1, 2, 3, 4. That's another point on your line. And then once we have 2 points, we connect them with a straight line. We're done. That's pretty much what we did last time, right? The problem was a little different because it kind of instructed us what to do, but there's nothing new in this, right? Okay, the next type of problem that we're going to look at is, well, let me say it this way. If I give you the equation, you should be able to graph the line, right? What if I give you the graph of the line? Can you give me the equation? So that's where we're headed now. So find the equation in slope-intercept form of this line. I think it's coming out pretty good. I have it set on the camera where it's really picking up the contrast, the black on white, so you can see it when you're watching it. So I just look like a black blob in the video, moving back and forth through here. It's kind of funny. All right, I need to give you a picture, don't I? Okay, so let's take our time to draw something here. How about so take your time to draw this. There it is. Now, can you help me? What are these points? What are the coordinates of these points? What's this one? 4, -2, and this one up here? -3, +3, right? So x, then y. Okay, so that's given to you, all right? From that, can we get the equation of the line? So we know that all lines can be written this way, right? And we can determine the slope if we know rise over run. And we talked about this last class, didn't we? We talked about there's a formula for slope. And then from that last class, we were also able to get B. Do you all remember that? Okay, so I'm gonna start this problem the same way we did last class, but then after we kind of work through it, I'm gonna show you there's another formula you can use other than this one that will get you to the same result. And you should be aware that there are 2 ways to approach this. But getting the slope is the same either way. So to get the slope, we use the fact that the slope is your rise, which is y2 minus y1 over x2 minus x1. What's this x1, y1, x2, y2? What am I talking about here? The coordinates of these points, right? So I need to label these. And does it matter which one I choose to be my x1, y1, and x2, y2? Does it matter? No. It turns out that either way you do it, you should get the same answer. So I'm going to just call this one up here my x1, y1, and then the one down here, I'll call it my x2, y2. So my slope should be y2. What's y2? -2 minus, what's my y1? 3 over my x2, which is 4, minus, what's x1? -3, right? What's the numerator here? -5, right? Over, well, it's barely coming out there. 7. So you have to be a little comfortable with sign numbers here, right? Take a negative number, subtract, all right? Turns into this. Subtracting a negative is the same as adding, so you get 7. So that's my slope. So I have this much of the equation, right? I have that much. How do I get B? How did we do that last time? How did we get B? Did we plug in 0, right? Yeah, what we did is we used the fact that if this equation has to be true, and I know what the slope is, right, then I can write this right now. -5/7 x plus b. And then I can use either one of the points to replace my x and my y, and if I do that, then I'll have b. That's the only thing left. Then I can solve for b. So let's go ahead and pick a point. Which one? You want to use the x1, y1? Yeah, the point that I'm going to use is this one. It was -3, 3. I'm going to use that in here. This will be my x. This will be my y. I rewrite the equation. It's 3 equals -5x, -5/7 times x. What's x? -3 and then plus b. And the only thing in that equation, the only variable in that equation is b, right? So, what is this? 15/7, right? Reminder, that's the same as this. And then multiplication of fractions is straight across. So 15/7. So this becomes 3 equals 15/7 plus b. Now what? Subtract 15/7 on both sides, so you're isolating b. So when I subtract 15/7 on the left side, I get, well, I'm going to have to figure out what that is. And then on the right side, it goes away. In order to add or subtract two fractions, we must have the same denominator. So I rewrite 3 as 3/1. And then I need to turn that denominator into a what? 7. So I multiply top and bottom by 7. That's the same as 21/7, isn't it? And then minus 15/7 equals b. So we get 6/7. That's your b. And now we put it all together. We take that b and we come back here, and I'll have the equation. Any questions? I'm going to write down the final answer here, but are there any questions on this? So the answer is y equals -5/7 x, and then plus b. B is 6/7. Box it up. Okay, now I said that there was another approach that we could use. So I'm going to kind of stop this problem, and then we'll come back to it, and we're going to kind of redo it. I want to share with you what's called the point slope formula. Remember, there were basically two ways we wrote lines. This is kind of a side note to remind you. That was one way we could write a line. Another way was this. That's what we looked at last class. This right here is a formula that you use if you're ever given a point and a slope. If you have a point on a line and a slope, you can use this formula. And it goes like this. y minus y1 equals m times, in parentheses, x minus x1. Where m is the what? Slope, and x1, y1 would be some point, the coordinates of some point that you have. So we can use this formula instead of this one if we want to. It all depends on what information you have in the problem. Now, if we go back to the problem we just had, we had worked out the slope, hadn't we? We worked out that the slope was 15 over 7? Oh, sorry, -5? -5/7. That's what our slope was, right? And then we had 2 points, right? And we happened to use that point -3, 3. But the way we did it is we tried to find that b, didn't we? Tried to find the b. Instead of doing that, let's use that instead. And let's see how, it should work out to be the same problem, the same equation, shouldn't it? Let's see what happens. So I'm going to rewrite everything here. It's y minus, what's y1 for me here? It's 3 equals m, which is still -5/7, and then x minus what? -3. So I'm going to have to subtract a negative, which is going to turn it to a plus, isn't it? So we have y minus 3 equals -5/7 times x plus 3. Now that does not look like the answer we got, does it? Not yet? Right, didn't we have -5/7 x plus 6/7? That was our answer? Okay, that's not there yet, is it? So what we have to do is we have to distribute the x through, or sorry, the -5/7 through, and then we have to bring this 3 to the other side. If we do that, we should get the same exact answer. So let's distribute. Y minus 3 is still on the left side. -5/7 x, and then what? What's -5/7 times +3? -15 over 7. So when you multiply 3 times this, it's really like a 3 over 1. So 3 on the top, 1 on the bottom. Now I can add 3 to both sides. I have the -15 over 7, and then adding 3. I can't add these things together until I have the same denominator, right? So I turn 3 into what? It'll be 21 over 7, right? So I have y equals -5/7 minus 15/7 plus 21 over 7. And then when you put these two together, you have -15 plus 21, which is 6, over the common denominator 7. So you get the same exact result. Now, on a test, I will not force you to do one way or the other. You can either use this formula or do the other one where you solve for b. It's kind of up to you. Any questions? All right. I know this is still a lot of review for some of you, but just hang tight. It'll get new eventually, hopefully. All right, how about this one? Find equation of line in slope-intercept form. Which one is the slope-intercept form? When I say give me a line in slope-intercept form, which form am I talking about? Y equals mx plus b, right? So I want you to give me the slope of the equation of the line in slope-intercept form if I give you this, okay? Here's what I'm giving you. The slope is -3/2, and the y-intercept is 2. Or actually, the 0.02. So I start with this. Do I know M? What's M? -3/2. What's B? Do I know B? Yes, I actually gave you the y-intercept, didn't I? So the B is actually just what? 2. So we're done? Yeah. Okay, that's somewhat trivial, isn't it? I mean, if you're given the y-intercept and the slope, you can go right to the equation, because that is B. Let's compare that to the same sort of problem. Okay, I'm going to leave all the instructions up here just like this, but this time I'm going to change this. I'm not going to give you the y-intercept. I'm just going to give you a point for -3. So can you find the equation of a line in slope-intercept form if I give you a point and a slope? Yes. Now, how can you do it? You can use point-slope formula, the one that I gave you just a second ago, or you can go and do the y equals mx plus b and try and figure out what b is, right? So it's up to you. So let's take a vote. How many of you think that you would just do the y equals mx plus b and find what b is? Okay, how many of you think you'd use the formula I gave you today, point slope? Okay, so we're about even, and then there's a bunch of people who don't care. So we'll just we'll flip a coin. Heads, it's y equals mx plus b. I was tails. We'll do the other one. Okay, we're going to use this one just because we haven't practiced with this one enough. All right, let's use that one. That's called the what formula? Point slope. It makes sense to use it because I have a point and a slope. It becomes y what? Minus -3, so +3, equals slope, -3 halves x what? -4. Am I done? Nope, I have to distribute. I have to solve for y in order to be complete here. So I have to distribute through here. Y plus 3 equals -3 halves x. What happens when I distribute this through here? Negative times negative is positive. Straight across I get 12. On the bottom I get 2. So 6, I get plus 6. Well, that's nice, no fraction. And then one more thing. Subtract 3 on both sides. So I get plus 3 when I subtract 3 from 6. And I'm done. Okay? Have I beaten this topic to death? Do y'all feel okay with this? I was hoping by me standing up here looking at you, I'd get more energy, but I seem to be the only one who has the energy. All right, well, then if no one's going to reply, then we'll just see if you can handle this. Find equation in slope-intercept form, okay, of line which is parallel to 6x plus 9y equals 27, but passes through the point -3, -5. Okay, so now in this problem, I'm asking you to put some of these ideas together, to think through. It's a little more involved than just, hey, here's the slope, here's the point, figure out the equation of the line. I do want you to find the equation of a line, right? I do want it in slope-intercept form, so I do want it to be y equals mx plus b. However, I'm not giving you the point and the slope directly here. I'm telling you that I want you to be parallel to this line. So there's some line out here. I'm not quite sure where that line is, but here it is. I'm just going to make it a, okay, let's say that's the line. That's not the line I want, right? I already have that equation. And then I have this point -3, -5, which is somewhere around here. I want the equation of the line that goes through this point that's parallel to this. So I want it to be, that's supposed to be parallel. I want that blue line. I want that equation. So how can we do it? What do you have, like very directly, what is one thing you do know about the line that you're trying to find? You know it's parallel, but you also have what? A point, right? You have a point. What do we need to graph a line or to get the equation? A point and a slope, right? Do you have the slope of the line? Not yet. How can you get it? Or tell me about the slope of the line that I'm interested in finding. Well, parallel lines have what? What's the property of parallel lines? They have the exact same slope. You're thinking perpendicular. Okay, so I know that the line, the slope of the line I am trying to find, the blue one, must have the exact same slope as this line. Do you know what the slope of that line is just by looking? Well, maybe, but how could we find the slope of this line? Solve for y, right? Turn that one into y equals mx plus b. Whatever the slope of that line is the slope that I'm going to need to use here with this point. Okay? So there's just a little more involved here. We have to realize that the slope of the line we're trying to find is actually hidden in this one. So let's go find it. I need the slope, right? Which is same as slope of 6x plus 9y equals 27. Solve that for y. So I just move the x term to the other side by subtracting it. And then finally, divide everything by 9. So y equals what? -6/9 is a fraction, but it reduces, doesn't it? 3 goes into each of those. So -2/3. X, then what? +3. Are we done? Is this the answer for us? Are we box it up and move on to the next problem? No, the only thing we're interested in here is what? The slope. That's it. This is all we want right there. We know to be parallel to this line, we must have the same slope as this line. So my slope of the line I'm trying to find has a slope of -2/3. So now here's where we are. So we know that m, the slope of our line, is -2/3. And we know that a point on our line is what? -3, -5, right? And now just do what we've been doing, right? Dot, dot, dot. I mean, you do it on your own, or you want me to do it? Would you like me to finish it, or do you think you could handle it the rest of the way? Do I want to? Well, I don't mind doing it. Okay, I'll finish it then. That reminds me of something my dad used to tell me. That's the second time I mentioned my dad in here, isn't it? Did I mention it the first day? No. know, about sitting in restaurants and, you know, my dad's still alive. I'm talking about him like he's not alive. But anyway, my dad used to say, you don't have to do anything, right? You don't have to do anything. You can choose to not do something, right? You don't have to be here. So I will do this. I don't know why it made me think of my dad, but all right. Maybe I need to give him a call. Negative 2/3 x minus negative 3. So that's just, now this is kind of like plug and chug, right? I'm taking my slope, taking my point, plugging in. Y plus 5. Just be kind of careful with the double negatives there. What do I get here? This is really a plus 3, isn't it? And then I distribute through with a negative 2/3, so be a little careful here. This is really a plus 3. When I hit it with a negative now, it'll stay negative, right? So it'll become minus 2. If you're having trouble with multiplying the fractions through like this or adding fractions, if you're having trouble with that, those are things people always have trouble with, but they are also topics that are not what this class is intended for. So that would be where you go over to that lab I was telling you about. You get the one-on-one tutoring over that developmental topic. Tell them, hey, I'm having trouble with this distribution. How is this coming out to negative 2? And they can help you with that. Okay, what's left? Subtract 5. Negative 2 take away 5. Negative 7. So our answer is y equals negative 2/3 x minus 7. If I graph this line, it should be parallel to the other line, and it should pass through the point that I was wanting it to pass through. Negative 3, negative, what was it? Negative 3, negative 5. I just realized earlier, didn't I plot that wrong? Didn't I write here and here? Yeah, it should have been down here. Oops. That's where we wanted it. Let's just say something if it's obvious like that. Okay. Now, I want to do the same exact problem. I'm not going to take it all the way this time, but I want to do the same exact problem we just did, but instead of parallel, I want perpendicular. So, find equation in slope-intercept form of line perpendicular, I'm just going to put perp, to 6x plus 9y equals 27, but through the point negative 3, negative 5. Was that a sneeze? I saw that. Let it go. Let it go. All right. Perpendicular. This is the only difference in the problem, isn't it? That's the only difference. But it makes a huge difference, doesn't it? Because now, instead of having some line sitting out here, and my point negative 3, negative 5 here, instead of trying to find that line that I had last time that was parallel, I actually want it to be perpendicular to this black line. So I want it to somehow come in through here, and I want it to cross that one there, right? Something like that. I want the red line instead of the blue line. So to make this happen, what's the only piece of information I need? I need the slope of that line, right? I already have a point on the line. I just need its slope. But its slope is related to this slope. How is it related? It's that inverse, but you have to change the sign also, right? We call it the negative reciprocal. So we already went through all the work a minute ago, and we said that the slope of that line came out to be, what was it? Negative 2/3. That's the slope of this line. The slope that we want needs to be perpendicular to that. So the slope of our line will be this fraction flipped over and change the sign. Since it's negative, I make it positive. We talked last time about how they have to multiply to be -1. Well, another way you can do it is just flip it and change the sign. And you can check right now. If you multiply those two together, you get -1. So now what I have is this. I have a slope, right? Not this one. I have this slope, and I have the point -3, -5, and then dot, dot, dot. You would just go through and use your formula again, and you get a different line, right? Questions? All right. Let me give you the homework assignment. We're done with 2-3. It's different than the homework assignment that's on your schedule. And just so you know, the schedule that I handed out last class, this is what we call a standard schedule. So the entire math department uses this book, and this is the schedule that we try and follow as far as what homework problems to assign. And I'll be pretty honest with you. This is a summer class, and I do things a little bit different in the summer, right? Because everything's so fast-paced as far as so much information's coming that I do trim off a lot of the word problems, and we just do a lot of the mechanical stuff. So that's why if you compare the assignment that I put up here to this, a lot of those like 109, 111 are not going to be on your assignments. If you want to do those, just do them on your own, or you kind of figured it out? Okay. So this is off of page 186, 31, 33, 39, 43, 49, 57, 63, 65. And then one last one, 86. If you go through these problems, it's pretty close to what I just did today, with the exception 86 I did last class, where it's where you find the equation if you have 2 points. So that's what this one is. This is find a line parallel, this one perpendicular, so we just did those examples. Then the rest of these are very much like what I did in previous problems. Okay, 2.4. 2.4. We're supposed to do 2.4, 2.6, and 2.7 today. We have a lot to do. So 2.4 is titled Functions. Functions. Now, a function is a very general math concept. It's a very broad topic. You could spend a lot of your life studying functions. In fact, one of the hardest classes I ever took in graduate school is a course called Functional Analysis, where it's all about functions. So we are going to do a very narrow look at what functions are, all right? So we're just going to focus on some very basic ones. But the concept of the function is always the same. Concept of function is this. You have a number, right? You start out with some number. Someone give me a number. 2. Okay, I heard 40, and then I heard 2, so I'll say 42. Okay, you start off with a number, and then from that, you send it through some function that does something to it, all right? And then it spits out a new number. New number. That's what we deal with in this class. right? Number goes in, number comes out. What the function does depends. You can define this function many different ways. So we're going to look at, in this class, we're going to focus on 6 functions. Right, 6 functions. We're going to look at what are called lines, which we've already done. We're going to look at quadratic functions. We're going to look at polynomial functions. Then we're going to look at rational functions. Then we're going to look at exponential functions. And we're going to look at logarithmic functions. Those are the 6 main goals of this class, is for you to have a good understanding of all those 6 types. But all of them follow this same rule. You have a number that goes in, something happens to it, something comes out, right? So if I take 42, I send it through some function, and it comes out, and let's say it's 84, what does it look like that function did? Doubled it, right? Is that what had to happen? No. So I could have said this. The function could have been like double it, right? It's like in words, that's what's happening. Like, here, bring me a number. Okay, double it, 84, right? But I could have also said what? Add 42 to it, right? Wouldn't adding 42 to 42 come out 84? Are these the same functions, though? No, because if I take something like 3 and I double it, I get what? 6. But if I say 3 and I add 42 to it, I have 45, right? So I guess what I'm getting at is just that functions can do different things, and by looking at one input, one example, and one example of the output, it's not enough information for you to really know what's happening, right? So someone has to tell you what this function is for you to understand how it works, right? Okay, number in, number out. The numbers that we plug in, all right? The numbers that we plug in, that's called the domain. The numbers that come out are called the range of the function. So whatever you're allowed to plug into this function, whatever it is called the domain. Whatever comes out is called the range. Now, it turns out that there are certain functions that you can't plug certain numbers into. The function can't handle certain things, which we'll talk about in a minute. But right now, I'm just trying to get the general picture of what's happening. Now, we do have an important rule with functions, that all functions have to follow. And this is the rule. Rule for functions. Rule for functions. To be a function, you must have that one input, is it okay if I say input? That means one in, right? For every one thing that you plug in, to be a function, must have that one input goes to one output. If I plug in a single number, to be a function, it must spit out a single number. You cannot have a function where it takes in a single number and it spits out 2 numbers or 3 numbers. That is no longer a function. So one input, one output. Got it? All right. Let's talk a little bit about domains. And I'm asking you a question here. What are things you have been told can't be done with numbers. What are some things that you've been told that you can never do with numbers? Can't divide by 0. That's one of them. Can't divide by 0. And we can talk a little bit more about why you can't do that in a second, but that's one of them. Anything else? Fortunately for us in this class, there's really only one other thing that we're going to look at. Has to do with like square roots. Can't take square root of what? Of a negative number. Square, I'm actually going to put, not only is this, you can't take a square root, you can't take any even root of a negative number. I'm going to get lazy and just put the number symbol instead of writing the word number. Those are the main two things that we've been told you cannot do in math. Never divide anything by 0. And if you try and take square root of a negative number, what happens? It actually, you may have seen, there is a way of doing it, but what happens whenever you try and do square roots of negatives? You get this thing called I. Have you all seen that? The imaginary unit. Remember I? Okay. I is not a real number. Everything we do in college algebra, pretty much we're going to stick with real numbers. So we are not allowed to take square root of a negative. All right? All right, so let's, do we want to talk about why you can't divide by 0, or are we just happy with that? We're all happy? Okay. So I'm still talking about domains. Let's give you some examples of functions. All right, if I give you an x, can you give me what y is? Yes? So if I give you x, it will come out and turn out to, you can then tell me what y is. So x is the input, right? X is the in, and y is the out. So we would consider this to be a function. The function is actually this right here. It's telling you what to do to x, isn't it? It's telling you to double x. So if I say for this particular example, you know, plug in 2, what does it spit out? 4, you know, if I say plug in 3, it spits out 6, right? So this is how we would be able to define the function. We have to have one variable that you plug in, and the other one is determined from that variable. Is there anything that I cannot plug into this? Is there anything that would cause that function to fall apart, for where you wouldn't be able to define it? What would 0 be? What's 2 times 0? 0 still, right? So that's okay. I can plug 0 in. How about a negative number? Negative 10. What's 2 times negative 10? Negative 20. That's okay. So we can sit here all day, no matter what. If someone gives me a number, I'll always be able to double it, won't I? So this function is defined everywhere, meaning that any number can come in, and then all these different numbers come out, right? Let's look at the range. Okay, the input right now, the domain of this is everything, right? How do I say everything in math? There's a couple of ways to say it. You can say all real numbers. Have you all heard that before? Okay, all real numbers. That's one way of saying everything. Another way of saying everything is interval notation, where you use the open interval that goes from, what is that? Negative infinity to positive infinity, right? Means every number you can think of between negative forever and positive forever. Plug it in, no problems. And then the last way that you can do it is by using what's called a double struct R. Double struct R, and this means all real numbers. So that's this right here, all real numbers, is this also. So y'all okay that I can plug any number in? Yes? Now tell me about what comes out. Do all real numbers come out? Can I get all real numbers? Will all real numbers come out? Convince me. I agree, but convince me all real numbers come out. Can I get 3 to come out? Yes? From where? Where does it have to come from? 1.5 or 3 halves, right? If I double 3 halves, double it, it comes out 3, right? So I can get that. So it becomes kind of, I mean, some people can look at it and say, yes, every number that's possible can come out. But there's another way of looking at it where you can see the range. You can see what comes out. And that's just by looking at this. What type of equation is this? It's a graph of a what? It's a line, right? Doesn't that look like y equals mx plus b? Yes? And so if I were to try and graph this line, this is my x, right? This is my input. The y is my output. And so what's the slope of this line? 2 over 1, right? The slope of this line is 2 over 1. What's the y-intercept? Since there's nothing there, it's 0. Right? There's no b, or b is 0. And so I would start at the y-intercept of 0, and from here I'd go what? Up 2 and over 1. And then I would draw a straight line, wouldn't I? How does that tell me that the range is everything? And how can I look at that and tell that the domain is everything? Well, take a look at the x's, right? If I pick an x right here, if I pick some number, I'm just going to arbitrarily pick x. Is there an output for that x? Where is it? Up here somewhere, right? If I pick an x right here, is there an output for that? Yes, right here, right? If I pick an x right here, is there an output? Down here there is, right? You see, for every x, I look up, do I see anything? Do I hit the graph somewhere? Yes. If I look over here and look down, do I hit it? If I keep going, if I'm way out here, sorry I'm off camera, but if I'm way out here and I pick an x, right? Do I have graph somewhere? It's way up there, right? But I hit something up there. So for every x, there's something on the graph. Therefore, every x is in the domain. That means all real numbers. How could you visualize the range? So let me ask you, does 2 come out of this function? Did 2 come out? Where did it come from? 1, right? Do you see that on this graph? If I say, hey, does 2 come out? If you come over here, it came from 1. Does 3 come out? Well, here's 3, right? Is there something over here? You know, I may not be able to tell what it comes from, but I know that it does come from something, right? Does 4 come out? Yes, right? Does 100 come out? Yes. How about negative numbers? So if I come down here to negative 4, does negative 4 come out? Yes. Comes from something, right? So what I'm trying to get at is that when you are talking about domain and range, there's kind of 2 ways to approach it. One is purely just algebraic. Just look at this and go, can I plug everything in? Is that okay? And the other way is, if you know what it looks like, you can look at the x's, look up and down, and then you can look at the y's and look left and right. We'll do more of this. Questions? Range? What can I say the range is? I want to finish this up. What's the range of this? All real numbers. So I'm just going to do double struct R. Let's do a different example. How about y equals x squared? Oh, I thought you had a question. So there's a couple of ways we can view this. Let's try and do it just by looking visually. For every x I plug in, is there a y that comes out? Yes? Are there any problems we're going to run into? Like, is there a number I plug in here that we won't be able to square it? Well, the two issues that we have to deal with are division by 0, right, or square roots. Do you see a fraction here that we have to be concerned about division? No? Do you see a square root? You see a square, but how about square root's this, right? So you don't have a square root. So we shouldn't have any issues squaring a number. Does that kind of make sense? So your domain here would be what? All real numbers. What about your range? The outs. Yes, what about 0 itself? That's right. So think about it. You've always been told if you square a number, right, that it has to be positive. Right? Any number, doesn't matter what it is. If you take 2, square it, you get 4. If you take negative 2 and square it, negative times negative is positive, you still get 4. So when you square a number, you should get positive. The only issue would be 0. And 0 squared is still 0. So the range of this would be everything larger than 0, right? How do we say that? We use interval notation, 0 to infinity, and then we use a bracket and a parenthesis. Now, bracket means you include 0, including 0. So 0 can't come out of this function, can it? And then everything else positive. So we go out to infinity. Now, how would we visualize this? Well, you would have to know what x squared looks like, right? This is not a line. It's what we call a parabola, which is something we'll talk more about today. And I'll show you what the graph of it looks like now, but I'll also give it to you later. The graph of this, if I plug in 0, I get 0, don't I? If I plug in 1, what does it spit out? What's 1? 1, right? If I plug in 2, what does it spit out? 4. If I plug in 3, what does it spit out? 9. Now, what if I plug in negative 1? You get 1. Negative 2, when you square that, you get 4. Negative 3, you get 9. You're up here. And so you get, it's curved. It's not a V, right? It's not sharp corner. It's curved. And you get this thing called a parabola. Now, look at the x values. If I pick some arbitrary x value, do I have graph when I look up or down? Yes, right? I'm going to hit that somewhere over there. If I move all the way out here, keep going off the screen, I have some graph up there, don't I? Same thing if I move negative. I've got graph. So my domain is everything. Do you see why the range is only from 0 to infinity, though? If I now look on the y-axis and pick some value here and look left and right, do I ever hit graph? I actually hit it twice, don't I? That's okay to hit it twice. Here I would hit. Any number up here I'd hit. What about down here? Like, pick any number down here. Look left and right. Do you have any graph? No. So if you don't have any graph, then it's not part of the range. Do you see the visual connection between domain and range? How you can associate it with the graph? No, I'm just some of the looks. All right. All right. We're going to kind of step away from the visual for a minute and just get back to how do we talk about domains just with the algebra. So far, both examples I've given you, the domain is everything, right? Let me give you an example of one where your domain is not everything. And for these, we will not talk about range. We're just going to talk about domain. So find domain only here. Find the domain of y equals x over x minus 4. So let me ask you right now, if I give you an x, can you tell me a y value? So if I hand you an x, a number, can you put it in here and then tell me what y is? Yes? Okay, so it appears to be a function. The question is, can I hand you everything? Or are there some things I can't hand to you? So could I hand you 0? Okay, if I gave you 0, then you would say, oh, that's 0 over 0 minus 4, wouldn't you? And then that would be 0 over negative 4. What's 0 divided by a number? That's 0. That's 0. We just can't have 0 on the bottom, right? That was the problem. So, yeah, if you look at this, the question now becomes, what will mess this thing up? Well, what will mess it up is if that bottom part, the denominator, right, is 0, right? So I'm going to just ask myself that question. When is that 0? If you add 4 to both sides, this would just be x is 4, right? I mean, you probably just look at it and you can see it's 4, right? But that's what I'm doing algebraically. I'm setting the denominator equal to 0, and then I'm solving, and I'm getting x is 4. And what I'm saying to myself is x cannot be 4, right? Because we do not want that to be 0. So how can I tell you everything is okay to plug in except 4? How do I say that? Okay, so we go back to interval notation, and this time I'm going to help you with the number line. This is what we're trying to say. Here's the entire number line, right? Here's 0. We have the number 4 here. We do not want that number, right? You can have anything else that you want. You can plug in both directions forever. Just don't plug that one in, please. So the way we do it is with an interval. We say everything out that direction, which is negative infinity. We use a parenthesis on infinity always, because infinity goes forever. Okay, so we can't put a bracket. Bracket means stop there. All right, and then where do we want to come to? 4. Do we want to include 4? No, so we put parenthesis again. And then we want to go from 4 on, so we say 4 with a parenthesis again, and then off to positive infinity. And so we have one interval which represents the left side of 4, one interval which represents the right side of 4. Anytime we have two intervals, we throw a big U between them, which means the union of those two intervals. That's your domain. Everything in this interval, pick any number here, and we're good to go. Pick any number in here, we're good to go. Following? Questions? Yes. Wait, negative infinity caret 4? Like this? Well, you could, you're talking about set notation, where you would say something like x must be less than 4. Is that what you're talking about, this one, or no? And then do it again, x is greater than 4? Oh, well, write it down on the board back there, and then I'll look at it. I'm using strictly interval notation on that. No, because that's not telling me anything about what it can be. What that's saying is that 4 is between negative infinity and infinity. It's not telling me not to include 4. It's just saying that 4 is between those two things, which is true, but it doesn't tell me to exclude 4. All right? If you're going to use inequalities, here's what it would have to look like. You would have to say x must be less than 4 or x must be greater than 4. That's what you would have to say. The x that you're allowed to plug in has to be smaller than 4, to the left of 4, or the x you plug in has to be greater than 4. This is called set notation. This is called interval notation, and we're going to use interval notation completely in here. So if this is all like, what the hell is he talking about? I would, again, get with me or get with the tutor and say, hey, I need a little refresher over interval notation because we're going to use it in my college algebra class. We're going to take a break here because it's about time, but hold on. Before I do that, this infinity symbol, right? The infinity symbol, infinity is not a number, right? Do you all understand that? Infinity is an idea. It's the idea of going in some direction forever. And it actually can be, there's a way that you can kind of see where that symbol could have come from. All right, everyone agree that this is a little strip of paper that we would all probably agree it has like two sides to it, right? I mean, you could argue that the edge is a side also, but you know, take the edges out. Just this is one side, I turn it over, there's another side, right? So if I hold this, I pinch it with my fingers like that, my index finger and my thumb are on separate sides of this page, right? Index finger's on one side, thumb's on the other. Okay, if I take this strip of paper and I twist it one time, this might be a little too thick, twist it one time and then put the edges together like that. Okay, then I get this shape thing. Do you see it? It looks a little bit like infinity, kind of, right? Now, does this strip of paper have two sides? So if you follow my index finger around and come around, you will actually be on the same side that your thumb is on, and then you come back around, you'll be back to your index finger. This is an example of what's called a Mobius strip, and this is an example of a one-sided surface. And so if you were to walk along this surface, you could actually walk forever along the surface, couldn't you? You just keep walking. There's no end, which is kind of like the infinity symbol is like a never-ending continuum in one direction. If you ever meet a real math dork, like myself, they might refer to infinity as lazy 8. Yeah, he's laying down, chilling, taking a nap. It's real bad humor. All right, take a break, y'all. Let's say it's 3:13. We'll say 3:23. We're back. We're back. All right, we're gonna still talk about domains and ranges, but before that, we're going to just make sure that we understand what's called function notation, and then I'll get back to the domains. All right. So with function notation, if I write down something like y equals 2x, we said earlier that that looked like a well-defined function, right? You could plug in an x, it would spit out a y. But sometimes I want to let everyone know that what you're looking at is a function. So the way to let you know it is a function without you having to know anything else about it is to replace the y with f and then in parentheses x. And we call that f of x. That's the way we read that. So if I were to be reading this out to you, I would say f of x, right? F of x equals 2x. So that means my function depends on x. If you go back to the picture we had, remember I had the function in the middle? Function, I can call that f. What goes into it is x, right? What comes out of it is some number. We're not going to call that y anymore. We're going to say it's whatever I get when I plug x in. So this is important to realize that the name of the function is actually f. F of x is the output that you get when you plug x in. So there's a distinction. A lot of students think that this is completely different than this, or that, that they are the same, but it's actually two different things. F's the name of the function, f of x is the value of the function at a given value x. So if I plug in 2, what happens? It goes through the function, gets doubled, right? F doubles it, and then it comes out f of 2. What's f of 2, though? Is 4. Okay, so this is the notation. F, I'm blocking it. I'm sorry. I'm going to start paying attention now. I'm going to stay up against the board like this. And all right, so anytime you see something like this, that means that you have a function. Now, I can use a letter, something other than f. Okay, I could have, if I wanted to, same problem. I could have called it h of x is 2x. And by doing it that way, you still are now kind of being told, because of this notation, that this is a function. Function means one input, one output. Got it? I could even have something like the Robert function, right? I could name it Robert. And if you go into anyone that's going to do like business or accounting or things like that, we actually have functions that we use a lot in those courses. Things like C of x, like cost functions, or like R of x, revenue functions, P of x, profit functions. So that letter sometimes has greater meaning depending on what class you're in. In a college algebra class, we normally use F, G, H, lowercase, right? Okay, now, get back to domains. Find the domain of this. F of x equals 2 over the square root of 3x minus 1. Do you see any issues? Do you see some things that we could possibly cause some problems here? You have a square root, and you actually have a fraction, don't you? So there's actually a double whammy in this problem. You have to worry about two things. First, you can't have anything under the square root be negative. Do you agree? So there's two issues. First issue, first concern is that I can't have a negative under the root, right? That means what's under the root? What's under the root? 3x minus 1, right? That cannot be negative, right? Which means it must be greater than or equal to 0. Do you all agree with that? This is called a linear inequality. And to solve a linear inequality, all you have to do is isolate x. So I'm just going to move things around. I'm going to add 1 to both sides. I'm going to divide by 3. So what I'm saying is, so far, in order for this thing to be okay, for this function to be able to handle what I plug in, I need to make sure that the x value I plug in is greater than or equal to 1/3. Follow? That's only the first concern, though. The other concern we have is what? The denominator itself can't be 0, right? The denominator itself. If this whole denominator turns out to be 0, I have division by 0. So here's my second concern. Second concern is that the whole denominator cannot be 0, right? So even though this says does not equal, I want to try and treat it like it's an equal sign, and let's just do things to both sides of the equation. How can, if I'm trying to figure out what x is here, how can I get rid of a square root? Square both sides, right? Square both sides of the equation. If I square the left side and I square the right side, what happens? Left side becomes what? 3x minus 1. The right side, what's 0 squared? 0, so I still have this. Now this is just a linear equation, right? Not an inequality, an equation. And now just move things around. Oh, I forgot to put the not equal. So move the x to the other side, or the 1 to the other side, and divide through by 3. So what we're saying is, in order to avoid division by 0, right, I need to make sure that x is what? Not 1/3. Do y'all follow that? What was the other thing from the first concern that we got? X had to be what? Greater than or equal to 1/3? So now we need to combine these two pieces of information into one final answer. This one says our x has to be bigger than 1/3, right? And it can be 1/3. This one says, well, wait, hold on. If you allow it to be 1/3, I'm going to divide by 0, and that's going to be a problem, right? So what do you think our answer is? X must be what? Strictly greater than 1/3, right? Without the equal sign, because this one says I can't have equality. Now, in interval notation, what is that? Here's 1/3. I cannot be 1/3, but I can be anything bigger than 1/3. So how do I do that with an interval? Parenthesis, 1/3. Parenthesis, because I don't want to include 1/3, all the way out forever to infinity. Make sure on intervals, just be aware that when you write an interval out, you write it in the order that you would read it from left to right also. So I go from 1/3 to infinity. I don't put infinity before 1/3. So it's left to right. This is the domain, okay? That's the answer. So that's an example of a problem where you actually had two things you had to look at one time. Let me show you a slight variation of that problem. So here's another example, find domain. What if I had this? H of x equals 1 over 3x minus 1. That's very similar to what we just did, isn't it? Except we don't have the square root, right? We don't have the square root, which means we don't have to concern ourselves with that part of it. The only thing we need to make sure of is that that part is not 0, right? The denominator can't be 0. And if you go through and move things around like we did a second ago, you get x cannot be equal to 1/3. Do y'all see that? So what would this answer look like in interval notation? Everything except that number. So now, if we look at this one, it would be everything over here and everything over here, right? So we would write it this way. I'll put the answer up here. What is it? Negative infinity to 1/3 union 1/3 to infinity. Do y'all see how that picks up everything except 1/3? It jumps over that one point. Everything except that. One more slight variation, new problem. Find domain. Let's use g of x equals square root of 3x minus 1. So we had this earlier, right? But it was down in the denominator. Now it's not in the denominator, so we don't have to worry about division by 0. What we do have to worry about, though, is what? No negatives in there. So that means what's in here has to be greater than or equal to 0. And it can be 0, right? Square root of 0 is 0. That's okay. And if I move things around here, x must be greater than or equal to 1/3. So we can be 1/3 this time, right? So how would I represent this answer in interval notation? Everything from 1/3 bigger, right? Including 1/3. Bracket this time, because I want to include it, right? I want to include the 1/3, and then to infinity. So the use of brackets and parentheses isn't like a coin flip. I mean, it matters. It depends on the problem itself. All right, does that give you kind of a good little variety of the different types of things? I mean, those are the only things you have to worry about, square roots and division by 0. If you were, well, nobody is supposed to really be going on and do more math in here, but if for some reason you change your mind, then there's all sorts of other functions out there that you have to worry about domains issues with. All right, a couple of other things. I think you'll like this. This usually, students find this next concept pretty easy. In fact, they've asked me to just have a test full of these problems. And okay, domain, sorry. Determining function, domain, range from a graph. I should say determining in here if it is, okay, if it is a function, what the domain of it is and what the range of it is from a graph. So I'm gonna do a couple of examples to just get us started here. I would like for you to take a look at this graph, and I'd like for you to tell me if this graph, say that's 1, say that's 1, let's say that's -1 over here. So the blue is the graph. Is that a function? Is it a function? So if I have it, remember function meant for every input there's an output, right? For every in there is an out. Well, can I plug this in here, something right here? Does something come out? Right there, right? For every input that I have, is there an output? Once I get past 1, there's no graph, right? That simply means that the domain stops at 1. Okay, the domain ends here. And over here, after -1, the domain ends. So, but within the domain, is there something there? Yes. And there's only one thing, right? I come out here, go up, there's only one answer. So the way I can tell if this is a function is by doing something called the vertical line test. Have you all heard that before? Vertical line test? Vertical line test, all you have to do is draw vertical lines. And when you draw the vertical lines, if you hit the graph more than one time, it's not a function. So for each line you draw, you can only hit once. So this red line hits it only one time, that one hits it only one time. And that just means, look, for every input there was an output. Every input there was an output. So the vertical line test says, if you draw vertical lines and you hit it no more than one time, it is a function. So what I would say here is this is a function. All right, that's my first conclusion. It is a function. What's the domain of it? So where is the graph drawn? from x value -1, you have things all the way until you get to 1, right? So what I'm going to do is this. For domain, I'm going to say -1 to 1. Now, should I include -1? Yes, because we're assuming that there's a point here at the end and a point right here. So -1 to 1, we include them. How about range? Now we're talking about what comes out of this. So yeah, you want to look left and right. You want to start looking this way and talking about when you hit the graph. You hit it all the way till you get up to 1, right? But if you go below 0, there is no graph. So it only goes from 0 up to 1 for range. You see the difference? Domain, you're looking this way. You're going back and forth looking up and down. Range, you're moving on the Y looking left and right. So our range should be 0 to 1. Do we end at 440? Yeah. Yeah. I wish we could. Next one. Is this a function? What's its domain and range? It is not a function. Good. Because if you draw a vertical line and it hits here, it'll hit twice, which means as you try and plug in an x, it's telling you to go here and here. So it's trying to take an x to 2 places. Not allowed. So if you don't have a function, you can't talk about domain and range. Right. So this is just, the end of this would be it's not a function. How about this one? The arrow means it keeps going forever, right? That direction. Is it a function? If I start drawing vertical lines, I'm only going to hit it one time. What about domain? So if I go to left and look up and down, I'm hitting something, right? Way over here, I'm going to hit something way down there. Keep going, way down there, it's going to be there, right? If I come over this way, start looking up, I'm going to be hitting it. So the domain is everything. What about range? What about range? Start moving on the y-axis and look left and right. Am I going to hit it? Yes, yes, yes. How about down here? Yes, 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 yes. So it looks like everywhere I move on the y-axis, I get something. So it is a function. The domain is everything, which in interval notation, that's the interval notation for everything, although I've been using the double struck R. And the range should be everything again. Is a circle a function? No, fails the vertical line test, right? One last topic in this section, and then I'll give you the homework, and we'll try and cover one last thing. Evaluating functions. Oh, I'm going to pass the sign-in sheet around. You'll notice that on the sign-in sheet is last name Bass here? Bass? Okay. Okay, so you'll see on the sign sheet, you should have your name listed here. It's yellow if you were here last time. It's pink if you weren't. That was on the 10th. Now, today's the 12th, so just initial, just a little initial right there next to your name, and that's how I'll take attendance every day. So evaluating functions. All we want to do here is practice plugging things into functions and getting things to come out. That's all this is. So let's start with an example. Let's say I give you a function, f of x equals 2x squared. Start off pretty basic here. I would like for you to find, first of all, what is f of negative 3? So what would happen if you plug negative 3 into this function? You would square, right? You would do 2. You would square negative 3, and you square it before you multiply, right? Order of operations. So square that. That's 9. 9 times 2 is 18. Everyone comfortable with that? What about this? What's f of c? So all you're doing is replacing the x with c, right? So you get 2c squared. See here, when I had f of negative 3, all I did was I came up here, I replaced the x with negative 3, and then I got a number, right? Here, I actually plugged in, I didn't plug in a number, I plugged in a letter, didn't I? And it spit out something with that letter in it, right? So what we're getting at here, what we're trying to do is see if it's okay for us to try and plug things in that aren't necessarily numbers. How about this? What would f of negative 7c be? So you have 2, right? 2. And then we're replacing x with what? Negative 7c, right? So I need to put negative 7c squared, don't I? And now when you square negative 7c, you have to do negative 7c times negative 7c, which is positive 49c squared. And then you still have 2 out front, don't you? The important thing is that the squared here is acting on everything you plugged in, right? So I have 2 times 49c squared, and what's 2 times 49? 98c squared. So you get 98c squared. Okay. Try a little bit more here. Same function, okay? Same exact function. I want you to try this one. What would f of negative 3/7 t be? That's a t. So 2 times what? Negative 3/7 t, but then squared. What's negative 3/7 squared? 9 over 49. And then t squared would be t squared. So I have 2 times 9 over 49 t squared. What's 2 times 9 over 49? 18 over 49. So this is equal to 18 over 49 t squared. Do you see what I'm saying by evaluating functions? Evaluating functions it can be more than just plugging in a number. You can actually plug in expressions and then still get some algebraic operations to carry through and get an answer. One last one here, and then we'll move to a different function. What about what's f of 4c minus 5? So I'm replacing x, right, with what? 4c minus 5. That means that 4c minus 5 has to get squared, doesn't it? And the 2 is going to be sitting in front of it. When you square 4c minus 5, that's what, 16c squared minus 25? When you square a binomial, you have to FOIL it. That means you have to do, so this is separate work here. I'm doing 4c minus 5 times 4c minus 5 again, right? That's what I have to do. And therefore, you have to do this, 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 this. It is incorrect to just square each one and put a minus sign between them. That is not right. Who's going to volunteer to make that mistake on the test? Anybody want to volunteer to make the mistake of squaring? No volunteers? Okay, good. FOIL this out. What do you get? 16c squared minus, see, 4c times negative 5 is negative 20c, and then negative 20c again, and then plus 25. I'm probably off my camera, but that's okay. Combine these together, these two become negative 40c. So over here we have 2, and then the 2 is going to have to distribute through. But let me just write down what this is first. 16c squared minus 40c plus 25. And then come through with a 2. $32c squared minus 80c plus 50. That's what we get. Okay, your homework for this section comes off of starts on page 201. It's 35 through 57 odd. That's odd. That's ODD. Okay, ODD. Don't freak out too much. 35 through 45 is just looking at the graph, doing vertical line tests, domain and range. So that's like, 5 or 6 problems that aren't that bad. And then 47 through 57 are finding domains where I give you the function. So that's going to take a little work. And then do number 71. Okay, we are skipping 2.5 in the book, and we're going to 2.6. This will be it for today, all right? 2.6, we're not going to even try for 2.7. In fact, I think I might just skip 2.7 outright. So the title of this section is A Toolbox of Functions and Transformations. A toolbox of functions and transformations. Y'all know what a toolbox is, right? All right, good. All right, so when, what are the common tools in a toolbox? A wrench, hammer, screwdrivers, right? The tools that most people know how to use, right? Most of the time? That's what you would expect to find in a toolbox? Well, when we say toolbox of functions, what we mean is these are the functions that most people that have to deal with math have to kind of have and know how to use. So these are the functions that everyone here is going to need to know visually. When you see it, you're going to need to know what it is. All right? It's like you pick up the hammer, you say, this is a hammer. I hit nails with this, right? You don't confuse a hammer with a screwdriver. So these are the ones we need to know what they are, know what they look like, know how they behave. And there are 5 or 6 of them. Let's see, hold on. I forget how many this book does. 1, 2, 3, 4, 6. All right, the first of the 6 toolbox functions is called the identity. Now remember, a function has to pass that vertical line test. Remember that? It also should have some domain and range. I'm going to give you the function itself first, algebraically, meaning without the picture. F of x equals x. The identity function, why do you think they call it the identity? If I plug in 2, what does it spit out? If I plug in 5, -10. So whatever goes in is identical to what comes out, right? It leaves it unchanged. Identity. So the graph of this, if I plug in 0, it spits out 0. I plug in 1, it spits out 1. I plug in 2, it spits out 2. I plug in 3, it spits out 3. And what you get is that perfect diagonal line, right? What's the slope of this line? 1. You can tell from right here. Remember, this is like y equals mx plus b. The slope here is 1. So there's the identity. I will point out that the identity function passes through the origin, doesn't it? That dot 0, 0 does exist on this function. That becomes useful later, but let's just all keep in mind that that point exists, right? Okay, the next function, I'm going to go in the order the book has, is the absolute value function. Now, the absolute value function looks very much like the identity, except that instead of plugging in a number and spitting it out, it spits out the absolute value of that number. So if I plug in 2, it spits out 2. If I plug in -2, it spits out +2. Right? So it just always spits out exactly what you gave it, but the positive version of it. So how would this graph look? If I plug in 0, I get, if I plug in 1, 1, 2, 2, right? So doesn't it look just like the identity? This way it does, right? But when I try and plug in -1, what does it spit out? 1, and then -2 spits out 2. So it goes like this in this direction. And it creates a V shape, right? A V shape. And that is the absolute value function. Does it also contain the origin as a point? 0, 0 does live on that graph? All of the toolbox functions are going to contain the origin. So that's why I'm kind of pointing it out. All right, next one. How's this coming out on that video? The squaring function, and it does exactly what it says it's going to do. It squares things. So this is x squared, which later on we'll study these in more depth. That's a parabola. But it's a very, very special one. It's the one that if I plug 0 in, I get 0 squared is 0. If I plug in 1, we get 1. Plug in 2, we get 2 squared is 4. And so this is what I drew earlier. It's a U shape, right? The important thing is to not confuse it with the absolute value. It is not a V. It's curved. It's a U. And it also contains the origin. The next one is not the squaring function, but the square root function. The square root. And so what it does is whatever you plug in, it takes the square root of it. Now we actually run into some danger here, don't we? Because you can't take square roots of negative numbers. So whenever I draw this, can I plug 0 in? Square root of 0 is 0. Can you take the square root of 1? What's square root of 1? 1. So we have this point here. Square root of 2, can you take the square root of 2? You can, but does anyone know what it is? It's like 1.414, something like that. Whatever, who cares, right? 2, 3, 4. Can you take square root of 4? That's 2, right? So we'd be up here at 2. So the next point's out here. And then what's the next one you would be able to take square root of? 9, and that would be up at 3. So it looks like this, and it's curved. Okay, it's curved like that. Now, can I put negatives in? Can I try negative 1? No. So the domain, right, is cut off here, so that's the graph. That's it right there. All right, we have 2 more. The next one is the cubic function. And instead of squaring, it cubes. So whatever I plug in, it cubes that value. It times itself 3 times. So what would 0 cubed be? 0 times 0 times 0, it's still 0. So I do have the origin here. What would 1 cubed be? 1 times 1 times 1? Still 1. What would 2 cubed be? 2 times 2 times 2 is 8. It's way up there, right? 3 cubed, 27, right? 4 cubed, 64. So, I mean, you start taking off pretty quick. So it looks a lot like a parabola, but it's going to grow, or like the squaring function, but it grows extremely fast. And what if I plug in negative 1? A negative times a negative times a negative, right? When you do it 3 times, it stays negative. So instead of being like the squaring where it comes up on this side, it's actually going to stay going down. Negative 2 cubed would be negative 8. Negative 3 cubed would be negative 27. So it's going to dive down this way really quickly like that. That's our cubing or cubic function. Last one. The cube root function. F of x equals cube root of x, not square root, cube root. Can you take cube roots of negative numbers? Yes. Can't take square roots, can't take fourth roots, can't take even roots of negative numbers, but you can take a cube root of a negative number. So let's try this. What's the cube root of 0? 0 itself, right? So there it is, that magic point's always there. And then, what's the cube root of 1? 1. The cube root of 2, no one's going to know that. Cube root of 3, cube root of 4. What's the first cube root you're going to know? 8, right? Because you have to think of a number that multiplied times itself 3 times gives you 8, right? 8 is 2 cubed. So the cube root of 8 is 2. So this is 1, this is 2. So I have a point over here. And then this one goes like this. Very fast, it goes this way. But what about negatives? Remember, square root ended here, didn't it? But now I can actually take cube roots of negative numbers. So it's going to go this way very fast like that. As an example, the cube root of negative 8 is negative 2. Those are the 6 functions that everyone here has to be familiar with as far as what they look like. All right? I'm wondering how much more I can squeeze out of you today. I'm looking at you, and it's looking like the wheels are coming off here. This class is what, 2 hours, 40 minutes. I told you on my Cal 3 class is 3.5 hours, right? 3.5 hours. It's a long class. But that's more exciting. Everyone wants to be in that class. It's like Calculus 3. They're all math people. They're all gung-ho about it, you know? No, normal semester, hour 40. This normal semester is hour 15. Yes. Pardon me? It depends on how many times you're meeting. It depends on how many weeks it's for. Twice a week for the full semester. Is it a lab? Yeah, that's probably what it is. All right. Can we just one last push here at the end? Yes? Those are the 6 toolbox functions. If I put one of those on the board, everyone should know what it looks like as far as the picture. All right? The goal now is using those 6 functions to be able to create more general functions from those using what are called transformations. So transformations work as follows. They work as follows. Transformations. Right. Let's say you know what a function f, remember f was the name of the function, we don't say f of x. Let's say you know what a function f looks like. In other words, you know its graph, okay? So like one of those toolbox functions, you should know what they look like. So let's just say you do. Then, here's what we have, comma, then, here's what we have. First type of transformation. If you take that function and you add a number to it, the result that you get is you move the whole picture of that up by c. So take some function you already know what it looks like, and you add some number to it, like you add 10. What you're going to do is take that whole picture and you're going to move it up 10. That's how it changes the graph. That's how it transforms the graph. I'm going to do a bunch of transformations, and I'm going to do a bunch of examples. Okay, what do you think happens if you subtract it? You're going to go down. Okay, the result, down by C. And I hope that kind of makes sense. Well, yes and no, because you can have a shift. If that's the only shift there is, if that's the only transformation there is, then yes, that will be an intercept. But you can have combinations of shifts. You can move up, down, left, right. As you'll see, we can flip and do other things. So that by itself, yes, but if it's combined with other transformations, it may not be the y-intercept. Good question. Okay, so that's adding a number to the function, right? I want you to notice where this adding took place. The function's sitting here, right? And the number we added was separated from the function. Compare that to this. F of x plus c. Notice where the c is now. I want you to look at that as being inside the function, near the x, right? Next to the x. What kind of shift do you think this is going to be? Left or right, right? These went up and down. These go this makes sense that it might go left or right. It actually goes opposite of what you would think, though. You would think that positive c would send you to the right by c, right? But with left and right shifts, you do the opposite. Up and down is what you would think. Positive is up, negative is down. But left and right, positive actually goes to the left. You just have to remember that. And then let me do the fourth one up here. What would f of x minus c then be? That would move you to the right c. So we have ways now of taking any toolbox function and moving it up as much as we want, or down as much as we want, to the left as much as we want, to the right as much as we want. Some other things we might want to do with it is put a negative in front of the function. Multiply by -1. Doesn't multiplying something by a negative number change the sign of everything? So everything that used to be up is now down, isn't it? Everything that used to be down is now up. So that negative in front has the effect of taking the whole graph and flipping it over the x-axis, or reflecting it over the x-axis. So this results in x-axis reflection, or if you like, flip. So if this is what function? The squaring function, right? If I put a negative in front of it, what it's going to do is reflect it down. So it'll reflect it over the x-axis like this. And so now it looks like this down instead of up. Okay? That's what it'll be. Okay, what about if I put the negative inside with the x? What's your instinct there? The y-axis reflection. And so with this one, what would happen? If the whole thing spins around the y-axis, right, if we reflect it, it just goes like this. And it would be the same function, wouldn't it? It just flips. And that would be because with the squaring function, if I plugged a negative in, it wouldn't have any effect because I'm going to square it. That's just for that function, though. Last thing, 7. If I put a number, I'm going to use a, and I multiply it in front of the function. This is the hardest one, okay? if I multiply the function by a number, then one of two things happens. It either stretches my function out vertically or it stretches it out horizontally. And it all depends on how big that number is. So I'm kind of running out of room, but I'll try and squeeze it in here. If the absolute value of A is bigger than 1, so whatever that number is, if the absolute value of it, if it's bigger than 1, then what that's going to do is, I mean, there's two ways to look at it. You need to look at it shrinking or stretching. So I'm going to try shrinking this semester and see how it goes. You shrink horizontally. What do I mean by that? If I said take this parabola and shrink it horizontally, what do I mean by that? Push it like this, okay? Which is going to make it look more narrow, right? That's the idea if the number is bigger than 1. If the number is less than 1, the absolute value is less than 1, then it's going to shrink it vertically. So what would this one look like shrinked vertically? Push it down, which makes it look wider. Does that kind of make sense? All right, those are your 7 transformations. So let's see if we can use these transformations to sketch something. I guess there's one good way to look at our situation. Where's the sign-in sheet? Did it get around to everyone? Anyone still need it? Okay, there is one good way to look at where we are here. We have a review for an exam. Let's see, we have an exam. 2. After today, we'll only have 13 more class meetings, if that makes you feel any better. 13. All right, here's what I'd like. Sketch this. Find the domain. Find the range. I'm going to do a couple of examples. All of the examples this is what I want us to do, okay? For the following examples. So here's the first example. I'll use F. Let's say we have this function. I would like for us to sketch this. Now, you open up your toolbox and you look in there and you see what tool, no, screw that. What toolbox function is this associated with? The absolute value. Now, it is an absolute value function, but it's got some other stuff happening, right? So what we want to know is what transformation has occurred from the toolbox function that we know. So here's the toolbox, or sometimes we call it the parent function. This is what the absolute value of x looks like, right? That's what that looks like, a v. And it had that one point right here, didn't it? Okay, all we've done to it is some shifting around. We've added a 1 on the outside, hadn't we? Adding a 1 outside the function does what? Raises it up 1, right? What does subtracting a number inside, notice it's inside the absolute value, what does subtracting a number inside do? To the right by how much? by 3. Remember, opposite of what you think. Do you see the difference between the number on the outside and number on the inside? Yes? My question to you is, does the matter in which I do it matter? Does the order in which I do it matter? So the question is, can I move up first and then move the whole thing right 3? Or do I have to go right 3 first, then up 1? In this case, it does not, but later it will, depending on the complexity of the problem. So we are going to start this by agreeing upon a method. The method we're going to agree upon is that you're going to do it kind of like an order of operations. You're going to always start inside the function next to the x. And the first thing you do is what's in here. So that's the minus 3, which means right 3, doesn't it? So what I'm going to do is on this picture, I'm going to do a little quick sketch. I'm going to take this picture and move it to the right 3. 1, 2, 3. And then I would have, I'm going to do it dotted, I would have this, right? Does everyone agree that that's the absolute value of x minus 3? That's just that toolbox function moved to the right 3. And now I move that whole thing, right? I'm outside of this now. I move that whole thing up 1. So take that point that was here, that came to the right 3, move it up 1. Here. And now you can draw your final picture. And you don't really have to worry too much about, you know, how perfect those lines are, how perfect everything is. What I'm going to be looking at when I grade these is your shift correct and is your picture correct. If yours is a little more narrow, that's okay. If yours is a little wider, it's okay. As long as it's an absolute value and it's been shifted correctly. The black one is the answer. Everyone see that? What's its domain? So move along the x-axis and look up and down. Oh, I look up here, I do hit something. Come over here, I'm hitting forever, right? So the domain of this one, I'm going to say capital D for domain, all real numbers. What's the range? We're looking on the y-axis. Do I have anything left or right here? When do I start hitting it? At 1. 1 is when I start hitting it, and I continue to hit until I get where? Forever. So how do I say that? Bracket 1, infinity, like that. Understand? Picture, domain, range. Let's do another one. How about f of x equals negative 1/2 x squared? What's our toolbox function? The squaring, right? Talk to me about the transformations here. It's a parabola, but what is this doing to it? What is it? What does a negative sitting in front of my function do? Flips it over the x-axis, right? What does the fact that this whole thing together is a number? It's like a. Remember we had to take the absolute value of a, and it told us if we shrunk it which way, right? So I want you to see two things. We are going to reflect, right, over the x-axis. And the fact that the absolute value of negative 1/2 is equal to 1/2, is that bigger than 1 or less than 1? Less than 1. That means we're going to shrink it which way? Shrink vertically. Push it down. So let me try and draw this. I start with my toolbox function. My toolbox function, let's say, looks like this. There is x squared. I need to flip it over the x-axis, right? So here's my flipping. Right? That's just negative x squared, isn't it? Just flip it right over. But now I need to shrink it vertically. That means I want to take it, vertical is up and down, I want to push it and shrink it that way, which is going to push the edges out. So it's going to open up, it's going to be wider, right? Like this. Do y'all see that? This one's my answer. There's two ways to look at shrinking vertically. You can say shrink vertically or stretch horizontally. And sometimes it makes more sense one way than the other. $430 or $440? $440. One more, I promise. That's it. We're done. Yeah. $427. We're done. Last one. Okay. How about this? Yeah. X. Well, you know what? Let's put a -2 out there just for fun. -2 x plus 2 squared minus 4. So what's your toolbox function? Oh, we didn't do domain and range on that last one, did we? Well, the domain is everything. All right, this was our picture. Domain is everything. Range. It's everything down here, isn't it? How do we say that? We have to be careful. We have to read it. Remember, on the domain, we read from left to right, didn't we? With range, you read down to up. So you go, with range on this one, you would say -infinity to 0, including 0. And domain would have been all real numbers. You want to describe to me what's the toolbox here? Squaring, right? This is the squaring function, so it's going to look like this. Where do I start? What's the first thing I should do? This +2, which moves it left 2. And then what does this do out here? Flips it and stretches it vertically or shrinks it horizontally, either way. And then after you're done with all that, the whole thing comes down 4. So what I'm going to do is I'm going to do each one of those transformations. I'm going to draw a big picture. I'm going to do step by step. All right, here's my beginning, right? Here's x squared. I'm going to move it to the, we said left 2, right? Because of this, opposite of what you think, left 2. Now, flip it over because of the negative, like that. Then, because if you take the absolute value of -2, it's bigger than 1, I'm going to shrink it horizontally, which is going to make it more narrow, isn't it? I'll do a different color here. I'm going to really exaggerate that. I made it very narrow there. And then finally, down 4. So that point comes down 1, 2, 3, 4. Here it is. And now I can draw that like this. You'll see all those transformations. Left 2, flip, shrink, down. On this one, would the order have mattered? What if I would have gone down 4 first? Right? What if I would have gone down 4 first? Think about this carefully. Now, let's say I moved it to the left 2. I'm right here, right? What would happen right now if I try and flip it? It would be like this. It would be there. And that's not the same picture. So order of operations here matters. See, when we say flip it, we say flip over the x-axis. So imagine my parabola is like this. I have to kind of like imagine this whole thing the whole board can turn. So this whole thing comes like this, it comes up here like that. You see? So we have to agree upon the order in which we do things. We always work from the inside out. And that would be the last thing we do. Okay, homework for this. Page 237. We're going to do 1 through 101 odd. I'm just kidding. I wouldn't do that to you. Hold on. It's only a few problems. Let's see how you do with this. 31, 33, 34, and then 63 through 73 odd, and then 75 through 87 odd. Okay, so let me tell you real quick how these work. These three, you're given the graph, and you're asked to try and figure out what the function is. So like the shifts have been made, and you try and look at the, try and come up, kind of reverse engineer the function from it. These, it's matching. They give you a bunch of functions, they give you a bunch of pictures, you match the function to the picture. And then these last ones are like what I did in class. They give you the function, you move things around. You draw it, basically. Domain on this, we never talked about it. Domain all real numbers, range, negative infinity up to -4, including -4. Have a good weekend.